that will enrich or change the ratio of carbon-14 to carbon-12 and make it different from what it normally would be. That has to be taken into account. And here are some, and that's taken into account by using the carbon-13. So it's a very nice system that we have, that there is this other stable isotope, and we can use it to measure how much fractionation occurs, and then we can extrapolate that to the carbon-14 and make a correction. So in air, CO2 has a carbon-13 fractionation of about 8 per mil, this parts per thousand, and in trees it's about 28 per mil, negative 28 per mil. So those things have to be corrected, and that's part of the definition of BP before present. And then there was a second big revolution in radiocarbon. The first revolution was Libby's discovery of the whole technique. And then the second revolution, according to Irv Taylor, is the whole idea of calibration, the ability to calibrate these dates. And so we use tree rings or lake varves, and you get annual layers in both of these. You count the layers, and now you've got an independent measurement of how old the thing is. And then you go and date the tree rings themselves through radiocarbon, or you date carbon inclusions that are in the lake varves, and now we get a calibrated date. So this corrects for any small variations that were in the atmosphere. So this is a picture of the tree rings. Typically, it's a bristlecone pine from California, or European oak from either Ireland or Germany that is used. The oldest living tree is about 4,600 years old, which is in the White Mountains of California. But this range has been stretched by using fossil tree trunks and matching the tree rings. What's done is you find years that had unusually wide or unusually narrow bands, and you can match those up with fossil trunks and step the record back. And so now the tree ring record goes back about 12,400 years. And this has been cross-compared. This is a shot of a calibration curve. This is the uncalibrated date on the left, the date in BP years, and this is the calibrated date on the bottom. And you can see there are some ripples because the atmospheric concentration is not absolutely constant. But you also see this plot has 4 different sets of data on it from 4 different laboratories using 2 different tree ring records, and they agree quite well. So you can see that we have very good agreement. If somebody is miscounting these tree rings, they're doing it the same on different tree ring records. So we can be fairly confident, I believe, that these tree ring records are correct. Also, you notice that the correction is around 15% back here at the oldest date, about 4000 BC. We have about a 15% correction. So some of the critics want to say that these tree rings can have multiple rings per year, and so these numbers are all completely off. Well, you've got to postulate then that not only do you have multiple tree rings per year, you also have something changing the decay rate at about the same rate synchronized with it, so that the only error you have is about 15%. And that becomes very hard to believe. So I would say the accuracy of tree ring calibrated dates is quite good. This is an example of a calibration curve and how it's actually used. and it makes some strange effects in the dates that you get. Here's the raw date coming out of the measurement, taking an example of a 1,000-year BP. When that's calibrated with the calibration curve, one gets a non-Gaussian result with multiple peaks. And so typically this is how it's reported. They show the plot of the multiple peaks, and they give multiple confidence level intervals. So at 68% confidence, it's this date. At a 95% confidence level, it's these dates. So it makes it a little bit tricky to deal with the calibrated data. But we've extended the calibration even further. These are pictures of lake varves from Lake Sujetsu in Japan. And in Lake Sujetsu, there's diatom growth in the spring that causes light layers. The rest of the time you have dark layers in the lake varves. And these are counted just like the tree rings are. And then carbon inclusions, little pieces of leaf or other carbon inclusions are found in there, and they're dated. Other lakes also show similar things. In Scandinavia, there's differences, seasonal differences in the silt that's deposited. Now with the records from Lake Sujetsu, we can extend the tree ring record back to 45,000 years. So the lake varve record goes back here, and this shows how it matches up with the tree rings. What they did with the lake varves is they didn't count all the way back from the present. They started at about 9,000 years ago, and then they take the ripples in the calibration of the lake varves, match them up with the ripples in the tree ring record, and you can see that the match here again is quite good. The ripples reproduce themselves pretty well. And so we have a calibration now going back about 45,000 years. And again, I think it's fairly accurate. There are some differences with some recent speleothem dates. And so there might be some modifications to this curve in the future, but I don't think they're going to be radical. Some recent anomalies in radiocarbon. From about 1900 on to about 1950, the level was actually below the norm. The radiocarbon level in the atmosphere was less than steady state, and that's called the Seuss effect. It's because of fossil fuel usage diluting the atmospheric radiocarbon, and that changed the ratio by about 3% or so. And then in around 1960, the level in the atmosphere doubled because of atmospheric nuclear testing. And so now, since 1960, the level has been dropping quite rapidly. And we wouldn't want to do this test of the atmospheric nuclear testing to see what it did. But now that it's been done, dates since 1960 can be done at extremely high accuracy. You can get 1 or 2 year accuracy on radiocarbon dates. If you know something happened after 1960 and you're on the downslope of this curve, you can get extremely accurate radiocarbon dates. Now the next radiocarbon revolution is accelerator mass spectrometry. And Irv calls this a third radiocarbon revolution. It was invented by Rich Muller in 1976. And the idea is to use a particle accelerator as a mass spectrometer to count the radiocarbon atoms rather than waiting for them to decay and counting the beta particles that come off. What this does is it allows using about 1,000 times less material than Libby's method. We need about 1 milligram of carbon, or even less, versus about 1 gram of carbon for Libby's method. And in addition to that, it's about 1,000 times faster. So this made a lot of things possible that were not possible before. Why do we need an accelerator? It's because the abundance of radiocarbon is so low. This shows a mass scan